Okay, so let's get started. So we want to talk about curve sketching. The idea is that if given any sort of general function, we want to know how to sketch the curve, okay? And the basic idea is that we want to be able to find the max and mins and identify and locate them exactly. And then we're going to kind of fill in the rest of the curve. So there's some basic ideas that we want to use here, okay? We're going to start off with kind of talking about the general procedure for curve sketching. Okay, if you have trouble reading anything, I don't write as well on OneNote with this pen, so just let me know, okay? But it's the only way I can make a video. Okay, so here's the basic idea. First of all, I want to figure out what's my domain. That's the most basic thing, okay? I have to know what values of x am I even looking at. So we want to determine the domain of the function. So certain functions we never have to worry about, okay? Sine, cosine, polynomials is not an issue. But when we're dealing with roots or rational functions, we're going to have to be careful. Certain trig functions like tangent, we're going to have to be careful, okay? One of the things that kind of goes with the domain is the asymptotes. We want to look at the asymptotes too, okay? And generally, we're going to look at things like vertical asymptotes first, okay? Mostly because these is where the function has really dramatic behavior. Usually you're kind of blowing up at these points. So these are very important points. It helps to look at some things like symmetry, okay? What I'd like to know is a function odd? Is it even? If there is symmetry, is there symmetry about an axis, okay? A lot of times functions are symmetric that don't appear to be. So for example, if you're given a function like, f of x is equal to, x cubed minus x, that's odd. And because there's a line of symmetry about x equal to 0, okay? And it's useful because when you go to plot those points, you know that every point that has a positive value, the negative value has the same thing, except it's going to be the function to have a negative value, okay? So the fact that this is an odd function helps us. If you have f of x is equal to, x to the fourth, same sort of thing. I'm going to use the fact that this is even. But there are certain functions that are symmetric that don't appear to be. So for example, the function f of x is equal to 1 over x minus 3 squared for x not equal to 3 actually is symmetric. It's an even function about x equal to 3. Okay? So this has a line of symmetry about x equal to 3. And it's an even function. Okay. And if you're not sure, just make a change of variables. Say let u be equal to x minus 3, and you'll see you get 1 over u squared. Okay? So sometimes there's hidden symmetries or kind of buried symmetries that aren't so obvious. And I would kind of say these are really general features. At this point, we're not really doing any calculus. These are just very general features, okay? And if you wanted to, you could almost combine them into one step. The one thing that I tend to do next is I look at the endpoints. Of the domain. And even if there aren't endpoints, there are endpoints. If you have f that's on an unbounded domain, you think of plus and minus infinity as really the endpoints, okay? So I'm either going to want to evaluate f if there's a physical endpoint. I'm usually going to want to evaluate f at the endpoint, And if I don't have physical endpoints, I'm going to evaluate the limits at infinity. Okay? So either there's going to be an endpoint, or I'm going to evaluate the limit of f at infinity, one or the other. Okay? Now, one thing we haven't talked about yet that they bring up in section 5, that's really important, is this notion of oblique asymptotes. So one of the things that can happen, and I'll mention this later on, is that you may converge to positive or negative infinity, but the function itself may converge to another function that's infinite as x goes to plus or minus infinity. So we're going to introduce something a little bit new here. I'll put this in red. So we're gonna talk today about what people sometimes call oblique asymptotes. I think the book calls them sloped asymptotes. Oblique just means something at an angle. It's not a horizontal, it's not a vertical, okay? So once we have this out of the way, now we're ready to start doing calculus. So next, we want to locate the critical numbers. And all I'm going to do is I'm going to find my derivative, right? So I'm going to find f prime of x. And what I want to know is, are there any values of x for which the derivative is not defined or 0, right? And I want to find all the x such that either f prime of x, is equal to 0, or f prime of x does not exist. Okay? Once I locate the critical numbers, I want to figure out the nature of the critical number. So I know a critical number can be one of two things. It can be a max, it can be a min, or it can be a point of inflection. There's only 3 possibilities, right? So the next part I want to do is I want to figure out the nature of each critical number. In other words, I want to know for each critical number, is the critical number a local max, a local min, or an inflection point. Okay? And this is really up to you how you determine this. So we have 2 different methods, right? First derivative test, second derivative test, okay? And it's really up to you. Which one do you use? The one that's easiest. Okay. So we have here the first derivative test and the second derivative test. Try it again. So you're welcome to do this with the first derivative test or the second derivative test. The first derivative test has the advantage that it will always give you a positive result. It will always tell you what the critical number is, okay? So this has the advantage. If you kind of look at the pros and cons, okay? The pros of first derivative is you always get a definite answer, okay? You always get an answer. Second derivative, you might not, because if the second derivative is equal to 0, the test is inconclusive, right? So the cons are that this test can be inconclusive when the derivative at the critical number is equal to 0. Okay? The cons of the first derivative are that it might be difficult to evaluate the function at the test point. However, when you take into account the fact that usually you only want the sign, generally that's not a big con, okay? So the worst thing that can happen with the first derivative test is that it might be difficult to find test points where you can determine the sign of the derivative. The sign of f prime, okay? Generally, that's not a limitation. But I suppose you could have cases where that could happen. The pros of the second derivative test is you have to find the points of inflection anyhow. You have to take the second derivative anyhow. And it's also less time consuming. So if you can get the sign of just the second derivative at a single point, okay, then this is actually less work. So the idea here is that you have to take the second derivative anyhow. And it may be that getting the sign of the second derivative at the critical number is less work than doing two separate points for the first derivative on both sides. Okay, so it could be less work. So finding the sign of the second derivative at the critical point may be simpler than finding the sign of two derivatives, the two first derivatives. Okay? Those are kind of the pros and the cons. Generally, I like using the first derivative because it usually isn't that much work. Okay. Sometimes it can be a little problematic. Usually, it's pretty easy, and you always get a definitive answer. That's more important to me, really. Yes, sir. So finding the sign at just one point, the second derivative may be simpler. Oh, anyhow. Yeah, so you have to take the second derivative anyhow, because we're going to have to find the points of inflection. So since you have to do that work, you might as well do it and see if it's easy to evaluate the sign of the second derivative at the critical number. Then if it isn't, you can always go and do the first derivative. But it's 6 of one, half a dozen of another. Whatever you find easier. Okay? All right. Any questions on this so far? Okay, one last step. So knowing the critical numbers is not quite enough, okay? We need to do one more thing. So our last step is we're going to find the points of inflection. So we want to find the points of inflection. Now, one thing to be aware of is that you might say, well, when we find the critical numbers, but not all points of inflection are critical numbers. So that's critical, okay? So I want to kind of emphasize this. Okay. So the point I want to emphasize here is that not all points of inflection are critical numbers. A lot depends on how the curvature changed. Okay. So, for example, if the function is very, very flat at a critical number, so this is an example of a point of inflection that's also a critical number, okay? And we've actually seen these. So I could draw a function that maybe looks like this. Okay. This is a point of inflection. Okay. Curvature is changing from concave down to concave up. And if I draw a horizontal tangent, it's going to have a slope of 0. Okay. So at this number c, f prime of c is equal to 0. But it's very easy, it's quite common to have points of inflection that are not critical numbers. So for example, any time you're between a maximum and a minimum, you're going to have a point of inflection, and it doesn't have to be a critical number. So here's an example of a point of inflection that is not a critical number. So for example, if I have a max and a min, so here's a local max, here's a local min, notice that this function has to go through a transition. When I'm at a local max, right, I'm going to have to be concave down. When I'm at the local min, I'm concave up. So I know that the second derivative here is positive in this region. And I know the second derivative here is going to be negative. And so I'm going to have to pass through a 0. Okay. I don't want to say it's always the case between a max and a min, because it's easy to think of pathological examples where if you have a situation where there's a critical number that's a local max, but it's because the derivative doesn't exist, then it's easy to think of cases where you don't have points of inflection. Okay. But when you have a situation where there's a max and a min and the derivative's both 0 at that point, you're always going to have a point of inflection. That's guaranteed. Okay? So what we're going to have to do to find the points of inflection is we're basically going to have to find the critical numbers of the second derivative. Okay? So to find the points of inflection, the idea is that we want to find the critical numbers of the second derivative. In other words, I'm going to take the second derivative, set it equal to 0, or see if there are values that make the second derivative not defined. And almost always it'll be the former. It's very rarely the latter. If the second derivative doesn't exist, it's probably something beautiful about the first derivative. Okay? And those are the steps. Okay? And normally we don't follow them. We don't follow them so much 1, 2, 3. Usually you look at the domain, and then you have your choice what to do after that. Obviously, the first derivative work comes before the second derivative, okay? But you don't have to evaluate the limits at infinity until the very end. I usually have to do it in the beginning. So here's what I would say. I would say these are kind of written in stone in the sense that you always should do, say, these 3 first, okay? This doesn't really matter. The order of this can be done at any time. Blow this up. Okay. This can be done any time. Okay. And obviously, the critical numbers have to come before the points of inflection. Okay. And that's all the order we really have to keep. Okay. So that's the theory. Any questions about kind of the steps of what we're doing or why? Everybody's good on this. So let's go ahead and do a few examples. Now let's see, put the black. Okay. So I have a few examples they're homework-like problems, so I don't think you'll see any curveballs on the homework. Okay. So let's go ahead and sketch the graph. Of f of x is equal to x over x squared plus 1. Okay? I'm sorry, x plus 1, sorry. Not x squared plus 1. Okay. So who wants to start off? What's one thing we know about this function already? What is the domain? I'm sorry? Absolutely. So what should my domain be? What are all the values that I can put into this function and not do anything mathematically illegal? What do you think? Well, I can't. Exactly, right. I can't take the square root of a negative number, and I also can't have a 0 in the denominator, right? So I need for x plus 1 to be greater than 0. Okay, so that's kind of the relevant point here. Which tells me x has to be greater than negative 1. So the domain's going to be minus 1 to infinity. Okay? Do I have symmetry here? I'm not symmetric about anything, right? So there's no symmetry here. Let's see. What about when I go to, what about the endpoints? So notice I don't have any endpoints. This is an unbounded. But I'm going to look at the limit as x goes to infinity, okay? So I'm going to look at my endpoints here, which are going to be plus and minus infinity. So I'm going to go ahead and take the limit of f of x as x goes to minus infinity. And that's a limit as x goes to minus infinity of x over x plus 1. Does that make sense? And people are nodding their head yes. Yeah. So I can't get a negative infinity, so this is not my endpoint. I gotta be careful, right? I only have an endpoint at positive infinity because the domain ends at negative 1. Good. Okay. So what's going on at negative 1? So what I actually need to do, the correct endpoint, is that I have to approach negative 1. How should I write this limit? I gotta be careful how I write this limit. Can I just write x approaches negative 1? What do I have to write? Right, I have to approach from above, right? So this is what I actually want to write. So I'm approaching negative 1 from above. Okay, so what's happening here? How do I evaluate this? I have an infinite limit, right? What is that infinite limit? Is this a weekend thing? So, with an infinite limit, what's happening? We're really looking at the sun, right? I know this thing is blowing up. How do I know that? Well, as I'm approaching negative 1, what is x plus 1 approaching? It's approaching 0 from above, right? And what's this approaching? Negative 1. So is this approaching positive infinity or negative infinity? We're approaching negative infinity, right? If I kind of break this down, right, what's happening is x plus 1 is approaching 0 from above, and x is approaching negative 1. So this whole thing is going to be approaching negative infinity. Okay? So I know a little bit about the graph there. And the way to do that when you have ratios is just to break them down. Break each part down. Okay? If you're not sure, put in numbers. Just try some numbers. Here's how I might do it. Let me show you one last way. Here's one way that I might do it. I might replace x by minus 1 plus delta, where delta is a small positive number, okay? And I might put this back in and evaluate the limit as delta goes to 0 from above. So one way of doing this, if I use this substitution, okay, I can write this as delta goes to 0 from above of minus 1 plus delta over the square root of delta. Okay? And if that makes it any easier, then you can use something like that. In any case, we know what's going on at negative 1. So this is an important point. Okay, at infinity, what's happening? As x goes to positive infinity, now I have a really interesting case. So anyone remember from limits at infinity how we do this when we have a ratio? What do we do? I'm going to take the leading term. I think I heard leading term, right? So there is nothing on the top except x. That's the leading term. And on the bottom, x is my leading term here, right? So in the denominator, I'm going to use square root of x, right? Because x is the leading term in this expression. So I'm going to end up getting the limit as x goes to infinity of x over the square root of x, which is the limit as x goes to infinity of the square root of x. Now up to this point, we've just said that's positive infinity. But when you're graphing this function, this is actually useful information. Because what it's telling me is this function converges to this function. So this is what we're talking about when we're talking about oblique asymptotes. This function's an asymptote. How many of you remember when you plotted rational functions, how every once in a while you have an asymptote that is kind of approach a line? Does anyone remember that? Okay. That's exactly what's going on here. So the one way of answering this, the way that we know from before, is we could say that this is equal to infinity. But what I also want to note, though, is that the function. So I want to note that f of x approaches the square root of x as x goes to infinity. Why might I want to know that? Because I can sketch out the square root of x. And I know that function has to converge to that, okay? All right. That part looks good. So now let's go ahead and figure out the critical numbers, okay? So this is the calculus part, right? So the first thing I have to do is take the derivative. Okay. I know that's going to be what? A quotient. Okay. And I could write this, since I'm going to be taking the derivative of the bottom, right? I'm going to write it like this. And using the quotient rule, that's just going to be, well, we know what it's going to be. We don't have to write the whole quotient rule out. And then when I square the denominator, I'm just going to get x plus 1. Okay? And I don't want to find the zeros of this. So right now, I really can't work with this very well, right? This is kind of a pain to work with. So if I try to get rid of this negative exponent, I'm going to end up with something that looks kind of messy. I'm going to get x over 2 times okay? And that's kind of a mess. So what I'm going to do when I'm working with a numerator and I have a fraction in the numerator is I'm going to get rid of the denominator by multiplying the denominator over itself. So what I'm going to do is I'm going to multiply top and bottom by 2 times x plus 1 to the 1/2 power. And you can use square root, right? Either one's fine. And of course, the reason why I do that is when I distribute, I'm going to get rid of that denominator in the second term, right? So I go ahead and just multiply through. Oops, what did I do? Here we go. Okay, and I'm going to get 2. And when I multiply these two, I'm multiplying really the square root of x plus 1 times the square root of x plus 1, right? So I'm just going to get x plus 1, and then I'm just going to get x here. Okay. Okay, never mind. I was looking at my notes and I had written something else from before. Okay. All right, so now I'm ready to analyze this. I can go ahead and simplify this, okay? So I'm going to have 2x plus 2 minus x over 2 times x plus 1 to the 3/2. And I can simplify this x plus 2 over 2 x plus 1 to the 3/2. Okay? And that's going to be my first derivative. Okay? So now I want to know what are my critical numbers here. Do I have any numbers for which the derivative is equal to 0 or does not exist? Okay. So does the first derivative of x for any x? Well, yes, but those are outside of our domain to begin with, right? So we know that the only thing that's going to cause that derivative not to exist is if I end up having, 0 or a negative number in there. Okay. So the answer here is that there are no values in our domain. Okay. There are values for which that function is not defined, but they're already not in our domain, right? Okay. What about not equal to 0? So is f prime of x equal to 0 for any x in our domain? And the answer is no. Because the only value that makes the derivative 0 is the value of x in the numerator 0, and that's x equal to minus 2. That lies outside of our domain. Okay, so the answer is no, because f prime of x equals 0 only if x is equal to minus 2, and this value is not in our domain. Okay? So we don't have any critical numbers. There are no local maxes and no local mins. And I can look and see if there are any inflection points now, okay? And there probably is going to be an inflection point. So at this point we have no critical numbers. Okay. We know the function goes to minus infinity at x equal to -1, and it approaches the square root of x asymptotically as x goes to positive infinity. But in between, there's no other structures. Okay. So now we just have to look at the inflection points. So let's look for the points of inflection. So I know what the first derivative is. It's x plus 2 over x plus 1 to the 3/2. So now I'm just going to take the second derivative. And again, just use the quotient rule. So I'm going to have x plus 1 to the 3/2 minus x plus 2. And then I'm going to use the power law on the denominator. The 1/2 all over x plus 1 cubed. Okay. And I'm going to have a hard time finding where that second derivative is equal to 0. That's what I'm trying to find out, the point of inflection, right? I'm sorry? I'm taking the derivative of x plus 2, right? Let's see, are you talking about, okay, are we looking at this term here?
The first derivative, the denominator has a 2 in front of it.
Oh, sorry. I left that out, right? Yeah, thanks, okay. Yeah, it won't affect anything that we're doing, but it's good to have that in there. Okay, all right. Okay, now I'm gonna have to find, what I want to do is I want to see if there's any solutions to the second derivative of x equal to being equal to 0. Okay. And I'm going to have a problem because I have roots in the numerator. But I'm going to factor out a square root of x, okay? So the idea here is I'm going to factor out square root of x plus 1. And I'm going to take the 2 out also, because the 2 is just kind of getting in the way.
So there's actually 2 in front of the x plus 1 which we have in the numerator. So I actually take that.
I'm going to see that. Let's see. Let's just make sure. So how did I get that term? I took the derivative of the quantity x plus 2, right? Isn't that right? But that would give me 1, right?
Right, but since you added 2 in the first derivative, you added another 2 before the 3/2. You took the derivative of the numerator times the denominator.
Oh, all I've done is I've just factored out the 2 here. I'm not sure if that's apparent or not. Okay, so this is, everyone agrees this is my first derivative, right? Is that right? Let's just make sure. I make sure I didn't copy it down wrong. Okay, so that looks okay. And then I just factored out the 1/2. Okay, because this is just a number, right? I can factor that out. Okay, and then bring him back in at the end. Is that answering your question or not? Okay, so let's see. So what do you think should be here now? Let's see. Okay, let me just do it from the beginning. Let's just do it. We'll do it in slow motion. Okay, hold on, just to make sure. Keep me honest. Okay, so when I take that derivative, I'm just going to factor out a 2. Okay, so I'm just going to do this. The second derivative is d dx of x plus 2 over 2 times x plus 1 to the 3/2, right? And I'm going to factor out the 1/2 here. Okay. Whoops, x plus 2. All right. And then I'm going to go ahead and I'm going to take my derivative just straightforward, right? So I should have x plus 2 prime times x plus 1 to the 3 halves minus x plus 2, and then everyone agrees this is 3 halves plus x plus 1 to the 1 half, right? All over x plus 1 cubed. Does that look good? Everybody good on that? Okay. Okay, so now when I take the derivative of the first term, I'm just going to get 1, right? So I'll get x plus 1 to the 3 halves minus 3 halves, and then I'm going to have x plus 1, x plus 2 here. You guys are supposed to catch me. To the 1 half, right? Over x plus 1 cubed. Okay, I think that's what I had. I'm thinking that's what I had. Does that look good? So was there a problem? I'm trying to think of where the problem is. I think this is what I have, right? Or did I have something different?
So the theory of the student was just use the
And we can change the order of products, so that's not going to go in. Okay? All right? Everyone good? All right. So what was the problem? Was it the derivative of x plus 2 became 2? Was that what it was? Or
No, I just didn't realize you factored out the 1.
Oh, yeah. Okay, yeah. Right, and then everything would have changed because I would have had the 2 up here and then the 2 here and the square, yeah. It's always easier to factor out constant multiples. Otherwise, you have to go through a lot more arithmetic, right? Much easier. Okay, so now I'm going to go ahead, I'm going to factor out a square root of x plus 1. I'm going to factor out a 1 half, okay? So I'm going to get 1 half, and I'm going to get 2x plus 1 minus 3x plus 2. And then I'm going to get, and so I've factored out here an x plus 1 to the 1 half divided by 2. Okay? Principally because I can't have square roots when I'm trying to solve for the zeros. Okay, let me put that out of the way. And also I don't want that factor of half. So I can take out a factor of half and I'll get a 2 there. Okay? And that looks like that. If you have any questions, feel free to stop. Okay, so all I'm interested in are just the zeros, right? So really the only part I have to look at for this function is actually this part right here. Okay? When this second derivative is 0, the only reason why it's 0 is because that portion of the numerator is 0. Right? This part can't be 0, that part can't be 0, and that would make that 0. Okay? So I'm simply going to find the zeros for that function. So I'm going to go ahead, I'm going to set 2 times the quantity x plus 1 minus 3 times the quantity x plus 2 equal to 0. And I can simplify that. 2x plus 2 minus 3x minus 6 is equal to 0. And I'm going to get minus x minus 4 is equal to 0, or x is equal to minus 4. So this is kind of an interesting example. Because is that a point of inflection? No. It's outside of our domain. So we didn't have anything. We didn't have any point of inflection. We didn't have any local maximum. We didn't have any local min. Just a very boring function. Okay, so now I want to try to sketch this out, okay? And what I'm going to try to do, I won't do a particularly good job of it, but I'm going to sketch this function, the square root of x. Because I know as x goes to infinity, f of x approaches the square root of x, okay? And this is -1. And of course, if we go back to our original function, right, f of x was equal to x over x plus 1 square root of. All right? So here's what I know. I know that at negative infinity, I'm sorry, I know that at -1, the function goes to negative infinity, and it passes through 0. Okay? It goes like that. And the function goes up, and eventually it begins to converge to the square root of x. But it always remains concave up. If you evaluate that second derivative, you'll see that it's always positive. Okay, if you go back and you look at this numerator, this numerator is minus x minus 4. Okay, this numerator, this portion is minus x minus 4. And if you evaluate that, you'll see it's always negative. The function always has negative curvature. Okay, and so this is kind of a boring function, but that can happen. You don't have to have a local max. You don't have to have a local min. You don't have to have critical numbers, and you don't have to have an inflection point. This should be f of x. Okay, so what I'm trying to imperfectly convey here is that the limit at f of x goes to -1 is minus infinity, but it passes through 0, and then the function keeps going up. It's concave down, but eventually it's approaching the square root of x. It's going to curve down and eventually approach the square root of x. Does that answer your question? Right. So here's what I found out before. I found out that the limit as x goes to positive infinity. So here's what we figured out before. We figured out the limit as x goes to positive infinity of this function is equal to the square root of x. So what that means is that as x is getting larger and larger, this function is approaching the square root of x closer and closer. That's the idea. So this is kind of like, you could think of this as like a limiting function. In a sense. Our function is approaching another function as x goes to infinity. Yeah.
So, I may be asking the same question, but why are there two isotopes?
Right. So this is the function. Right. So this is the function right here. This is the function that f of x is approaching as x goes to infinity. Okay. And that's useful because it would be very difficult to know how to sketch this function. It would be very difficult to know what this function is doing as x goes to infinity. Does it? I mean, you know that the curvature is negative, so it's always bent over like this. But how does it go? Okay, that's kind of hard to figure out. Yeah.
So if I understand correctly, what we did is what we learned is that we can find, using the derivatives, when we take the derivatives, we can algebraically find the maximum and minimum by taking the derivative and then finding the zeros in this derivative. Yeah. And what is the second derivative?
That's called the curvature. So the second derivative, if you go back to that expression for the second derivative, and you look at all the points in the domain of the function, you'll see that the second derivative is negative. So remember we said that when the second derivative is negative, we said that the function is concave down. Frowny face. So this occurs when the second derivative is less than 0, and when it's greater than 0, it's concave up. Okay? That's useful information. That's important to know. You guys feel like you feel like you want to see a hard problem or another easy problem, or what are you feeling now? I would say this is pretty easy. I would say that it's long and tedious, but really there's nothing in here. I mean, the derivatives are just all using the quotient rule, right? There's nothing new in here. Well, yeah.
We're not like a real life application.
Well, first I want to work on the mechanics. Let's get the mechanics down first, and then we can do real problems. So, what about the mechanics? Do you want to see a hard problem, an easy problem, or do you got to solve?
Tesla is so hard.
What's that?
Tesla is so hard.
Let's see. Okay. All right, so here's a really fun problem. This is one of my funnest. F of x equal e to the x squared. You know what, that might be too easy. Nah. Let me think if I want to make it harder. Oh, okay, we'll leave it at that. So let's go ahead and work on that. Work on that and see what we come up with. See what we can say about that. Actually, I can't write it. So f of x is equal to e to the x squared. We want to sketch this out. Does anybody know what this function is, by the way? Has anyone ever seen this? Oh, I'm sorry. I went minus x squared. Sorry. F of x equal e to the minus x squared. It isn't very interesting. Has anyone ever seen this function before? Does anyone know what this is? This function right here. Has anyone seen this note? Yeah, Tobias, what do you think? But you guys wanted applications. This is an actual application. To me, this is my favorite function of all time. Here, I'll tell you what, I'll make it a little more interesting. Here, we'll do that. Minus x squared over 2. This is the function. This is the probability density function for the normal distribution. It's the most important function in all of statistics in probability theory. So you want an application, see? So this is known. So you guys know what the bell-shaped curve is? Okay, this is the bell-shaped curve. So I'm actually giving this away a little bit, okay? This is the what they call the probability density function for the standard normal distribution. Which in my line of work is the most important function there is. If you do any sort of statistics or probability theory, it's the main function. Oh yeah, always. You have to. Okay, so let's go ahead and take a look at this. I'm kind of giving some stuff away, but still you want to verify. Don't believe me. I could be wrong. Right? I was wrong once when I thought I was wrong. Which makes it nice because I only have to analyze stuff on one side of 0.
The negative 2x squared.
Change was a pain, right? Okay, so let me kind of get you started on this, okay? Okay, so first of all, what is the domain? What is the domain of f? It's all reals. Okay, good. What else do I know? Do I have symmetry here? Sure. It's an even function, right? Charles. So here's the thing. We want to get some basic stuff first. Before we go to the calculus, we kind of want to get our bearings first. Like, what values of x does it even make sense? Notice in that last problem, you actually had critical numbers, but they were outside of your domain. So first, I just want to make sure I know I get the lay of the land, right? So my domain's all the reals, and I know that f is even. And that's going to be useful because that means that I only have to analyze stuff on one side of 0. Whatever I get on one side. Okay, now let's take the derivative, right? So f prime of x. How do I do this? Chain rule, right? So it's the derivative of the outside times the derivative of the inside. Okay? So the derivative of e to the x is e to the x, right? Then I take the derivative of that. Okay, so I'm just going to get minus x e to the minus x squared over 2. Whoops. Where did I go? Okay. So now I only have one critical number, right? Which is at x equal to 0, right? So x equal to 0 is a critical number. I can use the first derivative test directly, right? I can look at this derivative and say when I'm on this side of 0, what is the sign of the first derivative? Well, when I'm on this side of 0, this is going to be a negative times a negative, which is a positive. So the sign of the derivative is positive, the negative of 0, it's negative on the positive side of 0. So if I look at what's going on, right, this is going to be positive here and negative here. So I know I have a local max. And I can easily get the value by putting x equal to 0. So I know f of 0 is equal to 0. What's the only thing I need to find are the points of inflection, okay? And so I'm going to take the second derivative, set it equal to 0, and I'll leave it as an exercise for you to show it's 1 plus or minus 1 over the square root of 2. So to find the points of inflection, I'm going to set the second derivative equal to 0, and what you should find is that x is equal plus or minus 1 over the square root of 2. And you should find that the second derivative is positive, and then it becomes negative when it reaches the local max, which you kind of know that should happen, right? And then after you go over 0 and start to come down at plus 1 over the square root of 2, the concavity should become positive again. So you already know what you should see, but you can verify it with the calculation. So here's what I should see for the second derivative. This is minus 1 over the square root of 2, positive 1 over the square root of 2. I should see something like this, right? So here the second derivative is positive, negative, positive. Okay? That's what you should see. But verify. Okay. Pretty much all for today. You know, I'll give homework after we turn this one. We'll have new homework on this. Okay? That's all.
So because it's x plus or minus 1 half. So the positive is the down 1/3.
Right. This is the point of inflection where the function changes curvature. When it goes over 0, it still has a positive curvature. I mean, a negative curvature, right? But then it has to change. In order to have 0 as an asymptote, the only way it can do that is to change its curvature. It comes back that way. And that's the idea. Okay. Kind of looks like a little design. All right. Okay, good deal. I'll save this video if you want to go back and watch it, or torture your friends or whatever, and we'll have the review for the exam now.